Greg Asner, and I work closely with Joe Mascaro at Planet. I didn't put their names on this slide so that they have some deniability, but rest assured I thank them at the end. So I'm going to basically, among other things, completely abuse the term data fusion, and I kind of think I'm a little bit of a representative of the STAC folks over there, because my background is some bit of remote sensing, but a lot of data science, a lot of software engineering, and traditionally physics. So basically what I'm going to say is that ARD is really about user experience, and it's what it feels like to actually work with the data and making that easier. We've talked a lot about interoperability, and that can be a certain part of it. But when you go through, like going through Chris Holmes' definition in his blog post, those aspects, they're really the things that when you try and use this data, you end up getting frustrated by. And so he's just written them in a list and said we should fix them, and we should. And I think that's really what it would be nice to talk about and get further on. And I know that it's a big thing, but I'm just going to kind of talk about one of these things, which is co-registration, which apparently is boring, which maybe hopefully won't be at the end of this. But I'm going to talk about it in context of three kind of fun-ish examples in a relatively qualitative way, just as maybe a change of pace from all the other talks here. And in case you feel like you don't want to see the pretty pictures, this is really everything I'm going to say. So there it is. So I'm going to start with an example of refugees in Kenya. And this is basically my previous employer, Digital Globe, helped me out with some data access. And back then we were working with, one of our interns was looking at the growth of this refugee camp. And it's really dramatic, obviously. It's over a 10-year period. We see this huge influx of people from Somalia displaced, and the corresponding camp growth. Now, when trying to do some analysis on this, we pulled together some images and we're like, hey, wait a minute, this matches pretty well. And then we see another one and it kind of doesn't. And that's 4 meters, and this is like at 0.5 meter resolution, and so that's 8 pixels. Those 8 pixels are like, it's like, if it were just not there, I could just subtract these things and be fine, pretty much. It's just a frustration that happens when you're trying to do something with this. And now, we can go get our control point, or we'll find our little features, and we'll match them up, and we'll fix them, and that's what we do. But it's just a little bit of a frustration. That's where ARD as a user experience really kind of comes into play. And this is a best case scenario. This is a desert. It's pretty flat, and it's pretty much nadir, and we're fine. This is more typical. This is the Texas State Capitol in Austin, and we see a lot of different view angles. And even if you go to the ground, we're talking about errors of like 10 meters, which is like 20 pixels. So I bring this up now because it actually misrepresents the satellite. The satellite's actually a lot better than this, and I'll talk about that later. But, oh man, nowadays I'm doing forest ecology, so I need to talk about this really cool airplane. Our lab has this airplane. Its primary sensor is LiDAR. Basically, it generates DSMs. It generates point clouds, but turn them into DSMs, and you go to town. And the interesting thing about this, well, there's lots of interesting things about this. I'm going to just run through everything quickly. You can read the slide, but I've bolded this thing. It's post-processed using standard commercial software usually now. No like ground stations, no like special stuff. It's basically you buy something expensive from Trimble, and then you run it for a while. And it takes the pointing distance of that instrument and the pointing resolution of that instrument, and it takes down to like a few centimeters, which is amazing. That's absurd, right? Like airplanes going through the air and you're looking at something and you know where it is globally to like a few centimeters. I don't know. I thought that was interesting. And what they do with that is they take the height measurements and they make this kind of equation. And I'm new to the field, so I was trying to really understand it. And you look at it, it's basically a volume times a density, so a mass. There you get your carbon. We fix it because everything's power laws, and then that's how you estimate carbon actually quite well, apparently. So that is what like one of the things that my PI and Joe did, like, in a kind of seminal work, really. It's kind of a resolution of carbon mapping that hadn't been done before. It's really quite amazing. So what we're trying to do is scale up because as an ecologist on the ground, they have to go measure each individual tree, right? And so they can work at this kind of 1 hectare kind of level. And obviously 1 hectare is 100 meters on a side, and still as a human being that takes a little bit of time. The airplane scale is like 1.5 kilometer swaths, and you can get a bunch of data and process it on a supercomputer. You're all fine. But if you want to go to the country of Peru and get these height estimates, in other words, carbon estimate, or these height measurements or carbon estimates at country scale, you're going to have to do some sort of modeling. In order for this modeling to be anywhere close to possible, we need to get the LiDAR measurements and the satellite measurements to line up. And turns out they kind of do all right. So that's pretty good. But they kind of do all right because we're looking at 100 meter blocks. 100 meter blocks with 3 meter pixels in the planet case and 30 meter pixels in SRTM. But this is fine. This means that my project for the next year is not hopeless, right? Basically. So that makes me feel good. And really, because it came out of the box that way, and that's another big thing right here. Like this data being co-registered to this point out of the box makes my life hugely easier. I'm able to get promising results in less than 2 months of seeing the data for the first time. There's 3 different planet scenes, and I mean, say whatever, like the colors look the same, right? Kind of. It's fine. It's not. I'm not going to sit here and claim that I've made a model that does this, but I'm going to say that, well, we got somewhere pretty quickly. But here's the thing. We can also play around with positioning in another context, and that is taking the kind of LiDAR data that CAO collects, or in this case, the Center for Airborne Laser Mapping, and we can actually ortho our images to that itself. And I've taken out like occluded area. Oh God, what happened? Occluded areas in this thing, and what you'll see is that they line up. That you can get them to line up much better, even with like very crude processing of this data. Like I literally wrote some Python code in GBX notebooks, and that's it. What that tells you is that the sensor models on these satellites are actually ridiculously good, which means that, and that gets down to the pointing, the thing that like an airplane will the 3 meter, the few centimeter resolution that the airplane's able to get is really good, but the satellites themselves can get down to like sub-meter resolution if we're careful. What that means is that any individual collection, it's not necessarily about pulling out individual control points and matching relatively within a stack. We actually technically have the capability to just directly georeference things at a perhaps sub-meter level, right? And that's absurd. That's a huge enabling thing that would make someone's experience working with data much better. It just means it throws out a whole bunch of work. And what am I doing here? I'm really not saying anything else, but here are some kind of neat things that could happen if we focused on doing that. Like, for example, we could use expensive imagery from Digital Globe to rectify cheap stuff like a consumer-grade drone. We could pan-sharpened planet scope with worldview, which obviously would make some people happy, or a lot of people happy, and a few people maybe not. Maybe the building footprint data will actually line up with multiple scenes. I don't know. I mean, it seems like that could happen. And like I said at the beginning, change detection could be basically trivial. So I'll leave you with this one thing. First of all, thank you to all of my my PI, a programmer at CAO, and then Bill for giving me access to Digital Globe data even after I left. And this is a kind of cartoony picture. This is that last movie I did. I was calling it like poor man's hole filling. All I did was do like a median projection along Z of that thing. And what you can see is that if you tried to do this on a regular stack of images, it would look like complete garbage. And here it's like, I don't know, Pixar version of the Earth or something like that, right? 2 meters. It's like a 2 meter uncertainty. And I really don't have anything else to say. But I think that's kind of neat that, that things can get positioned that well out of the box. And I think that the folks in the next room would appreciate if part of ARD was just recognizing that something simple like positioning is an ease of use problem for people working with data. And we don't have to belabor the point, but you know, that's pretty much it.
Thanks, Pramukta. I think Rasmus is up next. Raring to go. Oh, do you have the adapter? Go. Here should be live if you want to test it out.
All right, you hear me?
Yep.
Okay. All right. So my name is Rasmus Houborg. I'm from South Dakota State University. So it's good to see some people. Usually it's just me and Corn. But we have plenty of time to do good science. So, and it is an exciting time to be an Earth observation scientist. Particularly now with the new paradigm offered by a constellation of CubeSats. It's really an exciting event and something that I see is going to really reshape Earth observation as we know it. So you have hundreds of CubeSats now in low Earth orbits, and thereby you overcome that classical trade-off between spatial and temporal resolution. So you can get daily imaging down to 3 meter resolution globally, something that was completely unimaginable just a few years ago. And it's kind of eloquently put by Freddie Mercury. It's a kind of magic. It really kind of is. So I just the science I do is just to kind of optimize the use of this resource and kind of realize its true potential. So that's what this talk is about. So I just want to give a quick overview of the timeline of key observation missions for land surface monitoring. There's been tremendous advances made over the last couple of decades. For instance, space agency missions such as Landsat has provided us with long-term invaluable records of land surface characteristics and change. But still, there's an ever-increasing demand for enhanced spatial and temporal resolution. And up to recently, that could only be met via expensive tasking of commercial systems, such as worldview, and even then on an area-limited basis. So I think that CubeSat constellations really offer an opportunity to kind of realize this potential and kind of meet the needed spatial resolution, the higher visit time, in addition to large area availability of data. So just to quickly go over the CubeSat story. So it's based on on a standardized modular building block design. It's very cheap to produce, based on commercial top-of-the-shelf components, and that makes it really economically feasible to produce in large numbers. And you can see, how this is kind of rapidly progressions in the number of CubeSat missions and the number of satellites being launched and being being prepared to be launched. And there's evidently a huge potential here. And you can configure these in a variety of different sizes. You have the 1U, which is 10 times 10 times 10 centimeters, less than 1.3 kilograms, up to a number of other, like 3U, 6U, and 12Us, to kind of increase the potential application areas where you can use these kind of satellites. So Planet is the largest operator of CubeSats in space, about, I guess, more than 175 satellites currently in orbit that adopt the 3U standard. It's about 4 kilograms each. This massive constellation has realized daily monitoring, as you all know, 3 to 4 meter ground sampling distance. So that's quite impressive. And compared to conventional satellite systems, the Planet resolution of 3 meter is really kind of superior to those. Landsat 30 meter, Sentinel 20, sometimes 10. And then you have to have the CubeSat, the Planet CubeSat at 3 meters. So you get a good kind of appreciation of the kind of resolution enhancement you get with this system and how that can be used to better monitor within field variations. At the same time, you overcome this classical trade-off between spatial and temporal resolution. So with Landsat, you have every 16 days an orbit, an acquisition. With Sentinel, you get maybe you get 4 images within that period of time, and then with Planet, you get 16, sometimes even more. Sometimes you have more than 1 acquisitions a day. So to kind of put it in perspective, it's similar to the frequency of observation you get with a 2-satellite MODIS instrument, but with a factor of 80 to 160 increase in spatial resolution. So this really increases the capability, the spaceborne capability for monitoring purposes. But as we have seen in a number of previous talks, it's not without limitations. The spectral resolution is not equivalent to that of Landsat and Sentinel-2. You have significant overlap in the visible domain. The bands are much broader. And this shows an average spectral response of a selection. I think it's 16 CubeSat sensors, and comparing that to Landsat 8. And you can see the shading kind of indicates the variability between the sensors, as each sensor has a unique spectral response. And in addition to this, the radiometric quality and the spectral resolution is not comparable to that of conventional systems like Landsat and Sentinel-2, which will result in cross-sensor inconsistencies and cross-calibration challenges. So as a result, spectral metrics, such as the NDVI, is not comparable or consistent across the different sensors, even after atmospheric correction. Let's see if I can find the mouse. All right. Even after atmospheric correction is 6S, you see that the CubeSat NDVI substantially underestimates both the Landsat and Sentinel counterparts. Whereas the Landsat and Sentinel are fairly cross-consistent. But this will introduce issues with sensor interoperability that I will talk about now. So in order to kind of fix this issue and trying to improve the quality and the utility of this high-resolution CubeSat resource, I developed a CubeSat-enabled spatiotemporal enhancement method called SESTEM. So it kind of exploits, a key feature is the use of conventional satellites, sensors, including MODIS, Landsat, and Sentinel, as a means to calibrate your CubeSat observations. It's a multi-purpose tool. You can use it for radiometric normalization, for phenology reconstruction via common metrics such as NDVI, and also as a spatial temporal enhancement mechanism for kind of enhancing biophysical properties such as LAI. And the latter component is, as I see, as a really important one because these quantitative insights are more valuable to many end users. Just a quick overview of the methodology. So inputs are MODIS and Landsat surface reflectances, in addition to CubeSat data either in digital numbers, top of atmosphere, or surface reflectances. The specific format of the CubeSat input is not really important for this methodology. It doesn't really matter much. And then I use MODIS data that has been downscaled to a 30-meter resolution. It's available on a daily basis, and I use that to quantify the change in surface reflectance between your CubeSat and closest Landsat acquisition. And this change information is then used to kind of identify and sample reference data from a selection of past Landsat images. And this is then used in a machine learning approach on a scene-specific basis to establish models for predicting Landsat consistent reflectances at the CubeSat resolution. And you can then turn that into NDVI, for instance, and get a Landsat consistent time series of NDVI, for example. It has also been extended to biophysical properties, enhancing them to the spatial temporal resolution of the CubeSat data. And that has also been extended to Sentinel-2 data using a bit more sophisticated, physically based canopy inversion approach. And this approach has been described in detail in a recent paper in remote sensing. It will take me an hour to explain it, so you've got to read the paper. System evaluations have been, in this presentation, I'm going to show 3 sites: an irrigated agricultural region in Saudi Arabia, the meat sites in Nebraska, in the US Corn Belt, and then an intensive farming area in Imperial, California, in Southern California, near the Salton Sea. So first, a few results on the Rate-O-Matic normalization component. So this is our study domain. In this area, you have an 8-day frequency of Landsat data due to overlapping swaths. And this then compares your CubeSat and Landsat NDVI. You see the frequency distribution on your right, and then you have the density scatter plots on your right, so on your left, on your right, all right. And you can see, the CubeSat NDVI, it's both as a function of top of atmosphere reflectances as well as 6x corrective reflectances. And in both cases, you see quite a big discrepancy. The atmosphere correction does reduce the bias and improve the correlations, but you're still looking at a mean absolute difference on the order of 25%. And this is just on one day. So then after applying system, the NDVI data aligns really nicely, and the bias is largely eliminated, and you get a mean absolute deviation of around 2%. And this methodology can also be applied to individual spectral bands, as shown here, for the blue, green, red, and near-infrared. And in most cases, in this case, I get an error of around 1%. So it really shows that these techniques offer a mechanism to produce Landsat consistent data with a factor of 10 increase in spatial resolution, and with a radiometric quality comparable to that of actual Landsat observations. And you can then also use this to reconstruct the NDVI time series, as I've shown here. This is an alfalfa field in Saudi Arabia over a 6-month period of time. And you have CubeSat data, NDVI based on top of atmosphere, 6S, and then your system corrected results shown in the time series plot. And you can see there's a lot of noise going on in the original CubeSat data. But then after applying system, you get a much smoother time series that's consistent with Landsat 8 estimates and quite nicely tracks the progression of these quite rapid growing cycles, as well as the exact, and you can also infer kind of the exact timing of your phenological transitions, such as harvesting. In the animation, you also get an appreciation of the kind of noise in the raw data, and that's even more evident when you do like a fast forward animation. So you have your your raw CubeSat data on your left, and then your system-corrected data on the right. So you kind of get a sense of the noise in the data and the capacity of system to correct for that noise and produce a time series consistent NDVI record. So this is the corn site in Mead, Nebraska. First thing you notice is that there's a big gap in Landsat, so if you just have Landsats, you really can't infer the phenology from during the reproductive stages through the senescence. So that's also, it's really powerful to have daily observations for that purpose. But again, the original data from CubeSat is quite noisy, and after applying system, you get a smoother curve that's consistent with Landsat 8, and quite nicely tracks the phenology that you expect for corn. So we also applied this to Sentinel-2 data as shown here. In this case, you have more frequent observations, clear sky observations. So the general trend of the crop phenology is better captured by the Sentinel-2 observations, but you still have fairly large gaps in your data record, including a 20-day period during green up, as well as a 30-day period during plant senescence. So in this case, the high-frequency CubeSat observation really provides critical information on your crop dynamics in between these Sentinel-2 acquisitions. And again, you see that the system results are consistent with Sentinel-2 data. I won't go into this, but it also, obviously cloud cover in Planoscope is an issue too, as we have heard before, and this system does include techniques to correct for that. I would love to look at the Planoscope the Planet 2.0 mask and see how it compares to what I've been producing. This is a fairly raw, it's a work in progress, but it looks pretty good, and you really need that kind of thing to make good time series. So just a few examples. So here I'm just kind of testing the interoperability of the Landsat and Sentinel-2 based system results, just overlaying the two results, and they're fairly consistent in time due to fairly similar spectral configurations. But then again, you do have BRDF effects and small spectral differences that ideally should be considered. So the ideal way of doing this is to use a single input to system, kind of a harmonized Landsat and Sentinel-2 data set, and that's something that I'm actually actively looking into doing. But they're fairly consistent both temporally and spectrally. And then this is a time series for the Southern California site. This is an 8-month period. You have 8 alfalfa growing cycles, so it's really a rapid kind of phenology going on here. And with Landsat, you're not going to be able to capture this. You need the daily record significantly improves your ability to capture these rapid growing cycles and harvesting events. And again, this is just a fast-forward animation, kind of showing the noise in the data and the ability of system to correct for this noise. And then this is the Sentinel-2 based results, just showing a single growing cycles to demonstrate the spatial and temporal advantages of using the Landsat, using the CubeSat data in this case. And then kind of overlaying these two, again, a fairly good consistency between the Landsat and Sentinel-2 based results. In most cases, in the beginning of the season, you have a bit of inconsistencies, and in this case, the Sentinel-2 based results provide a better constraint because of the larger number of observations. So the last few slides will be on the biophysical retrievals and the use of systems to kind of enhance retrievals from Landsat and Sentinel-2 in space and time. So this technique uses a machine learning approach to kind of build associations between the spectral data, the CubeSat spectral data, and your Landsat or Sentinel-2 biophysical retrievals, in this case leaf-fair index. And it does that on a scene-specific basis. And this is just one scene, one example. In this case, you get a fairly good match, around a mean absolute deviation of 5%. And then looking at a time series for a single point, the CubeSat LAI provides you with near daily information on your LAI dynamics, whereas the Landsat in this case is going to miss key events like harvesting in most cases. And the below plot shows a daily sequence, a daily green-up sequence, daily CubeSat LAI bounded by a Landsat LAI on day 206 and 213. So you can really get a sense of the potential of systems-based LAI estimates for kind of tracking what's going on in between Landsat acquisitions, and also kind of the spatial intrafield variations that is able to capture with these mechanisms. So if you only have Landsat data, you're going to miss a whole lot of interesting stuff going on in your field. And then it's also been applied to Sentinel-2 data or the meat sites in Nebraska, just quickly showing the resulting time series of LAI. The red circles are your Sentinel-2 based results, and the red squares, and then you have the circles are your CubeSat based results that kind of match your Sentinel observations, but then add both temporal and spatial information. Also done a preliminary validation against weekly in situ measurements from the meat sites in 2017. Get a fairly good, quite good an agreement with these, with a R-square of 0.92 and a mean absolute deviation of 13.5%. And if you only have Sentinel-2 data as seen on the right, you're not getting that same degree of accuracy because you have insufficient coverage during key periods of crop development. And obviously, the idea is to make this into kind of a near real-time production stream. I think that would be very useful. It's not an easy thing to do, and I'm not quite there yet, but this is definitely potentially feasible, and the system is being redesigned to kind of facilitate that thing. So at the moment, the reference data from Landsat or Sentinel-2 is only looking backwards in time. In the beginning, I looked both backward and forward in time, but this has been implemented to only look backwards in time to facilitate near real-time predictions. And then all the processing streams have been automated for seamless execution. The satellite data acquisitions can be done with a latency of 1, maybe 2 days, and that can be further optimized if you port it to the cloud. And the adopted machine learning techniques are being optimized and are generally well suited for big data analytics and cloud processing. So I'll just finish with a quick summary. System represents a cross-platform calibration approach, both for radiometric normalization, phenology reconstruction, as well as higher-level biophysical product generation. And in this way, you can think of it as a synergistic approach towards enhanced sensor interoperability and data harmonization. So a key feature is the use of these gold standard satellites as a means to kind of calibrate your CubeSat observation in order to realize their full potential. It is quite insensitive to the degree of cross-sensor inconsistency, so it can work with really noisy data with a lot of fluctuations, and the type of input format doesn't really matter. As a result, it can also be applied to other systems. It can be other CubeSats, it can be UAVs that require calibration in order to deliver useful products. And then a key feature is its translations into higher-level products. It's not mere production of spectral metrics. It also has the additional step of producing quantitative insights of real value to end users. And with that, I think I will stop and take questions.
Pramukta, you want to come up and Rasmus take the hot seats, as it were?
Sure. Just go get this.
I'm limping because my leg fell asleep. Sorry.
It looks like Ignacio has the first question here.
So thank you both for such interesting talks. I have a question for you, Rasmus, about what are the parameters? Is there any insight in the parameters of the models you're fitting to make the data interoperable, right? I mean, you're deriving essentially a set of heuristics and transformations that essentially calibrate essentially the CubeSat data, so it's harmonized and essentially anchored radiometrically by the Landsat and Sentinel. What's the variability or insight of those parameters as you move between different geographies or land covers? Have you looked into that?
Well, so it's really scene dependent because it kind of established the model on a scene specific basis. So I think that's both a good thing and a bad thing. It's a computational thing, but it's good in a way that it's really tied to that scene and it's specific and it's the characteristics of that scene. So that makes it quite powerful, I think, because it can adapt to new conditions in new scenes. And if you just apply a single model to all the scenes, you're going to have transferability issues with your machine learning models. And I won't have that in the same degree because I'm just doing on a single scene basis. So the parameters, the models are going to differ for each scene. Yeah.
Cool.
But it's a machine learning model, so it's a black box, I guess. Sounds like.
Cool. Yeah, I'm just interested in general about the insights about the variability across geographies that can help us calibrate better and understand the behavior.
Yeah, that's the thing, because they have that noise, so the model is going to differ between each scene and each day, right? Because it's not a consistently calibrated system.
Yeah.
I have a sort of related question. Thanks for the talks, by the way. They were really good. So you are able to fuse this Landsat data with the PlanetScope data, and it's sort of site-specific, but can you tell us, like, what's the amount of influence that a Landsat observation has, like, in time? How recently do you need one to be able to apply this kind of thing? Like, what would happen if Landsat stopped making observations? Could we keep applying the same models in the future, or would they break down? And then the same question is, like, over space, if you only had observations in some geographic area, how far away do you think, roughly, would the models hold?
Yeah, so the technique uses previous Landsat scenes to establish the reference data. So you can take a scene from the last summer and use that as the basis for establishing your model. But then the key thing is that I use the MODIS data to kind of infer the change over that time, because the surface conditions might have changed. But I'm using a selection of past images. For one pixel, I might be using reference targets from different Landsat scenes and kind of weighing that into my model. So it's also kind of reduces the noise in the Landsat data as it incorporates multiple Landsat observations in my scene-specific reference sampling. But if you have enough, a long period of time where you can sample data from, usually not having reference data is not an issue. It's just a matter of having enough past images to look at. So yeah, so it should work in most cases, really.
The obvious cheeky question, is the underlying system software open source?
Not at the moment. It's just a messy code by me, and even in IDL. But that's something that we can work on.
Yes, it was an open source in Python. I'd be very interested.
Yeah, I'm sure.
Thank you for your talks. That was really interesting. Kind of riffing on that same theme, though, a little bit. How would you like to see this operationalized in some way? And how do we get this to become something that's more routine and more than just a research project? How do we turn this into something operational? I'd like to hear your thoughts on that.
Yeah, I think that's important. It's obviously a big task, and it needs to be ported to a cloud computing framework of some sort. Also having direct access to the archives being planted would really help if you want to, because it's a pretty heavy data processing load. So at the moment I'm downloading all the data, doing the processing, so it's obviously time consuming. Yeah, and it takes up all my space on the computer. So it needs to be ported to a cloud environment, parallel computing for sure. But I think the design of it is that it's feasible to do that. But it will require some additional work. Yeah.
And do you have some insights into that you're willing to share in terms of why this is commercially valuable to industry, to a broader industry?
When you get a time series, you want to, if it's jumping up like that and you want to use it for detecting stress or disturbances, you want to know if the dip is due to stress or if it's due to contamination. So I think if you can remove the noise and you can improve the confidence in your data set, and then you can really use it for detecting these maybe quite subtle changes in the time series due to a stress-induced event, neutron limitation or water limitation or whatever. And I think if you have this noise removed time series, you can really use it for things like that. It's very valuable in a precision agricultural context, where you can relate the dips in your time series to changes in your field that needs attention.
Thank you for your presentation. Building on top of the previous question, I'm wondering how computationally intensive your fusion program is, and do you think it's feasible to apply that globally, or is it limited to a specific region of study?
Well, I try to optimize the techniques. The machine learning I use is a random forest implementation. It's an R code, the Ranger package is called, and it's quite fast compared to most other packages that I have come across. So, but then again, you need to apply it on a scene-specific basis. So it will add on in terms of time for sure. But I think in a parallel computing environment, it could be feasible.
Thank you.
So I want to flip to the first presentation. So you made the possibly obvious yet I think important observation that if people don't have to worry about spatial alignment in sort of their first phase of every analysis, it's like a really huge help. I think we saw some earlier presentations where even though Sentinel and Landsat are super well radiometrically calibrated and understood, that everybody had to start out by doing scene alignment, and in theory those are relatively low resolution sensors. It should be easy. So I guess I'm wondering, how do we move towards a world where everything starts out aligned? So I think you also made, I think I'm just talking a lot, but anyways, you made the point that I guess it would probably be in worldview that was the satellite pointing knowledge was good enough that they could get to like sub-meter just based on the ephemeris, but that is certainly not the case for Planet. So we have this need for basically some base of truth. I think the base of truth that's going into the Sentinel processing, the Landsat processing is obviously somewhat different, which is why they've got systematic differences. So how do we move as a community towards having one common set of truth? And I don't know if you've got the answer, but I wish I could get an answer to that question.
Well, yeah, I mean, I obviously probably don't have the answer, but I think I'm just starting to work with your guys' SkySat data, and I feel like I heard some rumor that there's like a video kind of capability, which seems to suggest that the pointing capability of that satellite might be just as good. I don't know if that's true or not.
Speaking out of school, I can say that the pointing control for SkySat is certainly not up to worldview standards, so we still have, and we're using as a base of control, we're using the same imagery we use for PlanetScope to, geolocate SkySat data. So, given that it's 5 times higher res, that's like a bit of a concern.
Well, I think that maybe that it's about producing a very good reference, I guess then, and I think that's a potential one-time cost and then a smaller incremental cost of updating. And even like a little bit tongue-in-cheek example of like pan sharpening across a daily updated source and a higher precision worldview source eventually you'll end up with some sort of ridiculous mistake. And that ridiculous mistake should be relatively obvious to pick out by eye, which means it should be relatively obvious to pick out by algorithm, right? At which point you know the location you need to like re-image or something like that. So I think there's there are update strategies like essentially tipping and queuing that can be done after processing that could allow us to maybe as a community have a high-res, well-positioned reference that we can use, and I don't know.
Okay, I totally buy that, and I think that we're not really going to have ARDs in the geolocated sense that we want until we've basically got a common community reference and how to fund and build and maintain, and I think how do you get it updated and everybody updates is like a totally difficult problem, but if we could, make significant progress on that, I think it would be like super foundational.
Just a bit of advertising on this topic. At DISA, on Sentinel-2 project, we have developed a global reference image, which we will use as a source of GCPs at global scale for improving the geometry of the product. So this GRI global reference image will be made available to expert users requesting it as from mid next year. So anybody interested to use this source of ground control points at worldwide scale may approach us. So
cool.
And we just another piece of information. We are collaborating with USGS, so they are planning to use this source of GCPs also in the Landsat geolocation process in order to bring the two missions closer together.
Awesome.
This is a related question for Ferran, but for the group, is this going to be available as part of Collection 2 processing, the new GRI?
That's a question for USGS.
I guess so, yeah. I don't know if anyone from USGS is here. Because that's the plan. That is the plan? Cool. Because that's a big step of interoperability, is at least making sure Sentinel and Landsat just we can put those pixels on top of each other to begin with. Yeah. Cool, awesome. More questions?
I didn't know, Franklin, did you have another?
No, I'm just trying to.
Oh, okay. All right, gotcha. Okay, well, thank you two again for the great talks and all the good questions. And I think there's still some fresh coffee out there. I think I saw come in like about an hour ago or something like that, and some cookies. I recommend the fudge stripes. So, and we'll see you here in about 10 minutes. At 2 o'clock, we'll have the next session.